Good afternoon, everyone. Hopefully that little bit of music is starting to become familiar, either with a sign of dread or hopefully a sign of joy. So back yesterday, we were talking about pointers and memory, and then finally at the end of class, someone asked, what is this useful for? And then we learnt about arrays. This was a simple data structure that we were going to use to store data of the same type. So we might have 5 integers, or 10 characters, or 12 doubles, whatever it happens to be. This would allow us to store multiple units of one type within a single variable and access them consecutively, or out of order, as we'll see soon. So let's imagine that we have a set of 3 characters. We have H, I, and then a /0. Remember, /0 is the way we're denoting that a set of characters ends, and in fact, this is going to be the secret for us for creating strings. A string is just a set of characters stored inside an array or pointed to by a pointer that ends in one of these separators, a /0. But we'll get more to that in one of our subsequent weeks. We can also represent our characters with their ASCII values, so in this case, high exclamation point /0 is 72, 73, 33, and then 0, of course, is our null byte. But it's all well and good to have this abstract representation. Most of you are probably asking, okay, so in the real world, what am I actually going to use these for? So no doubt, those of you who aren't in the class today have been paying close attention to my YouTube, where, as you can see, I've made it to the very top of the YouTube influencers list. Mr. Beast is unfortunately only number 2. He doesn't spend as much on his videos as I do. But the question is, how do we get a list like this in the first place? If I am Google and I have all the different influencers in a big list and I have all their different view counts, how do I actually figure out who has the highest view count of them all? And this is going to be our focus over the next week, figuring out a way to do this efficiently. So let's start by just doing a gentle introduction to the syntax in C that we might use to try and both figure out how many items we have in a given array, and then to actually look into the array to find an item that we might be missing. So let's start off with the array length one. Now this will be a pretty simple warm-up. And so I am going to begin with the way I always do. And now you'll notice this time we can now finally make sense of both of our arguments to the main function. So we have one integer argument and then one char star star argument. Now, char star star, remember a char star is a pointer to a character. So a char star star is a pointer to a character. But we can write this another way, and it's another way that hopefully you will have seen a few times, which is like this. Char star argv array. What this is essentially saying is it is a pointer to an array of characters. And as we just saw on our last slides, an array of characters is really a what? What data type is that? It's a string. So if we have an array, if we have a pointer to an array of strings, then maybe that's telling us that we have a collection of strings. And this is essentially what we're doing here. We're enabling our program to take in 2 inputs, one of which is a number, and one of which is a set of strings, or a list of strings stored in an array. And what they're going to be our command line arguments. So let's say you enter into our compiler, clang get int, just like we did last time over there, where we have our program that we're running, and then we have 3 subsequent arguments. What's actually going to happen is argc is going to become the number, let's see, 1, 2, 3, 4. We have 4 arguments, and then argv is going to be an array of strings. And what strings will be in it? The first string will be clang, the next one will be get int -c, the next one will be -o, and then finally we'll have get int. We'll see a little more how to use these momentarily. So let me first check. Let me first actually create the array. So I'm going to create an array of integers, and let's call this nums. Um, 11, 25, -1, that's perfectly fine. And now we have a bit of a problem if we want to figure out how many elements are in this. Because if we're using a pointer, we could start a pointer. Let's say we have an int star pointer that points to the very start of nums, because we know that that points to the very start of nums. And now we have a problem where even if we move our pointer on, so let's say I do pointer plus plus, I've got the issue where I don't know when I've actually finished this array. There's nothing to tell me how many items in the array there are, because I could keep doing pointer plus plus, and go out beyond the end of the array. So this is why in a string we actually have the /0 at the end. It's a marker to tell us when the array is over. So let's do that for now and pretend that our array is an array that can only have positive integers and negative integers excluding the number 0. So one way that we can tell how many valid items there are in it is to loop through it. So let's create a loop for int I equals 0. I is, well, that's not going to work because we don't know how many items are in it in the first place. Okay, so let's scratch that. Let's start with a variable I that's going to start at 0. The 0th index of the array, because we're computer scientists, we always start at 0. Now let's go from there and create our while loop. While, and then I'm actually just going to do true. This will be an infinite loop. So somewhere in the loop, I'm going to need to have a way to make it stop. And remember, this is how I use the break command, is to say, well, if this condition is true, break, end the loop. So what I'm looking for now is if nums I equals to 0, well, that's the element that I said is going to mark the end of this particular array. So if nums I equals 0, break. And now I also need something to count how many elements in the array I've seen. Well, that's going to make sense to reuse I, because I is going to enable us to both index into the array at a position, but it's also counting how many times we've actually advanced. So if I do I plus plus here, every time that I advance one further in the array, I'm going to increment I, and then when the ith element is 0, then I'm going to break. And that'll hopefully give me how many items are in there. So let's do this just as a nice warm-up. Print I. And return 0. Ooh, and I will call this length.c. So clang. Let's do that now. Okay, now it compiles. Let's do length. There are 7 items in the array, so 1, 2, 3, 4, 5, 6, 7. It's gotten it correct. Now, there are also other ways of actually declaring an array. I can predetermine, I can tell it I want space for 7 numbers, and then I can individually fill the elements of the array with those numbers. So for example, I can now write nums 0 equals 1 or 12, nums 1 equals 34, nums, you get the idea. I can do that with all the elements of the array, and I can also set them similarly inside my loop. So now let's say instead of counting, I want to use my loop to fill the array. So let's have some variable, let's call it length. I'm going to call that 7. And now what I'm going to do is now I can actually use a for loop, because I know what the length of my array is supposed to be. So let's do for int I equals 0, while I is less than length, I plus plus. And now I'm going to just fill the array starting from the ith element all the way from when I is 0 all the way up to when I is 7. Is that right? No, why should it not be until I is 7? Need someone new. Yeah, go for it. Yeah, what's your name in the middle? Sujin? S-U-J-Y, Sujay. So why don't I go all the way up to index 7? Because I can only store from 0 to 6. So if it's an array of 7 elements, it's actually going from 0 to 6. So I've set that up correctly here, so I is less than length. And now let's do I squared. So this should have an element of the squares of all the numbers. And now I'm going to do one more loop just to print them all out. So let me copy that. Now printf, and that will be nums I. Then I'm going to do another printf with a new line after all of that has finished. So let's do that one again. Now I can see I get all the squares over there. Okay, great. So there's our warm-up exercise. But now we actually want to start building towards our problem of figuring out who the biggest influencer is, say, in a list of views. So you can imagine all of these numbers are view counts of different views on YouTube. And now what we actually want to do is find the largest one. So unfortunately, in this particular version of the array, it's already set up such that it's in order. But you can imagine that we could just get a list of videos in whatever time they've been posted. And now I need I'm going to have a number of victims today, so I need new people who haven't come down to the front before. So where did Abraham go? Put your hand up. Okay, you're down at the front. Let's just hope that this connects. There we go. Just speak into that, say hi.
Hi.
Okay, great, it's working. Okay, your next task is to put on the big brain. Now it's a little unstable, but you should be able to get it on. Okay, I'll hold the microphone for you. Put on the big brain.
Okay.
You feeling brainy?
Yeah, a little bit.
Okay, so see if you can hold the brain with one hand and hold the microphone with another. The brain needs a little bit of repairs. So to get us started to figure out how to actually search through an array of things and to figure out how to do it efficiently, we're going to practice with the phone book. Now, at least when I was born, these things were kind of useful. Right now we have a web search. But fundamentally, web search is doing a similar kind of task. We're looking for items for a particular item in a set of much larger items. So perhaps by investigating it using my white pages here, we're going to have some luck. So let's say that I am looking for someone with the last name Pam. So tell me what I should do.
You could start flipping till you see.
Okay, I'm going to start. Yeah. Hold the microphone up. He said start flipping. Okay, so I'm going to flip. Okay, that's not working. I haven't found Pam. Okay, I've got another idea. Okay, I'm going to open the first page. A baker, a barlow, a barlos, abandon, abandonwits, abakara, abate. I haven't gotten to Pam yet. I'm going to keep going. Abawaji, abay.
Or maybe start from the middle.
Start from the middle?
Yeah. Middle of the book.
Okay, you're going to have to hold the microphone up so everyone can hear you.
Start from the middle of the book.
Okay.
Yeah, and see whether P is on the first half of the book or the second half.
I see king is on this side, K-I, and closet on that side.
Yep, so it would be the first side.
So this is K, this is A to K over here, and on the other side is...
Sorry?
I'm looking for Pam, starts with P, right?
Yeah. So the first side?
So look in the first side, okay.
Yeah. Then you'd like...
The first side over here is Ker, I'm going backwards. P is after K, right?
Oh yeah, so second side.
Okay, the other side. And so what should I do? I'm going to start reading the names down. Kliman, Klimas, Klimskak, Klimek, Klimek, Kliminski, Klein, Klingen.
Yeah, then do the same thing.
What do you mean?
So just divide the second half by 2.
Divide the second half by 2.
Yeah. So
well, I guess I don't need this half anymore, do I?
Yeah.
Okay. Scott. Okay, Scott, Scotter, Scotty, Scotto, Scott Pross, Scott Price. Scott O'Scowan, Scrafani.
Yeah, so if P, you have to find if P is in the first side or the second side.
Which side is it in?
Up, so it's the first side.
Okay, so I guess I don't need this side anymore, do I? Okay. Now what? It's in this side.
Yeah, so just do the same thing until you find
okay. Pill.
Yeah, so it's Pam, yeah?
Yeah.
So start flipping page by page till you see a...
Page by page, okay.
Yeah.
Pilly, piddy, piduck, pigeon, pigeon, pierce, piery, pianist, pierce. Is that a good idea? What should I do?
Maybe just use the same method.
Same method, okay. Well, we don't need that half anymore. Now I'm at Newen and Nyo.
Yep, so second half.
Okay, second half. Don't need that. Do it again.
Yeah, just do it again.
Okay, Oshan, it's in this half. I'll open it halfway. Paxton, so it's before Paxton. I'll split it in two again. Paltov, okay. And I should be just about here now, so divide it into one more time. And I've got the right page for Pam. So that actually worked pretty quickly, didn't it, in the end?
Yeah.
Instead of having to go through the list of every single name in the phone book, by throwing out 1, 2, 3, 4, 5, 6 steps, I could get to the exact page that I wanted with Pam. So can we have a round of applause for Abraham? Yeah, you can. Unfortunately, you can't take the big brain home. You're going to have to solve the exam with your own one. But you're welcome to come and use it during tutorial hours. Okay, so this is our example of the difference that a different type of array can make for an algorithm. But one thing was kind of unique here. Why did this work for our phone book as opposed to an array of random items? What's special about the phone book? Okay, let's go behind Andrew in pink. Oh, no, Hassan's not here to run my microphone around. Pass it back.
Yeah. Because the names were in order?
The names were in order, so I knew that I could throw out one of the halves because it definitely wasn't in that half. And that's really our key insight, is that we can do better than just going through the entire list if our list is sorted. So this is going to be essentially the thing that we have to do in order to make our algorithm work efficiently, also for our influencer problem. But this gives us kind of a very difficult challenge, because now we have to figure out not only searching, but we have to figure out sorting as well. So the first thing I want to do is ask all of you, how long would it have taken if there are n names in the phone book to find the name I'm looking for? What was your name again, sorry?
Sharon. Sharon?
Sharon.
Yeah.
S-H...
S-H-A-R-A-N.
R-I-N?
A-N.
A-N. Sharon.
Yeah.
Awesome. And we can't hear you very well on the microphone, so you're going to need to hold it up nice and high. So if there are n items in the phone book, how long will it take me to find the name I'm looking for?
At most n.
So at most n, that's good.
On average, about n over 2.
On average,
Half n.
say louder.
N over 2.
N over 2. Why n over 2?
Just because the fastest time would be 1. And the longest you could take is n.
You're going to have to speak louder. I can't hear you very well.
Sorry, the fastest time that you could take is 1, and then the longest would be n. So the average of those two would be n over 2.
So tell me what happens in the fastest case. How do we? What is that case?
If the name is the first one on the list.
So if I'm looking for someone whose name is like Adi, A-A-D-I, and I open the phone book and I start at the beginning, and they're in order, well, the best case is I find it right away. The worst case is if it's the very last name. Again, though, it doesn't matter for this particular, for linear search, if it's sorted or unsorted. If it's sorted, then we can make use of our better algorithm that we just did. But if it's unsorted, we don't know where Adi will be. It might not be in the first page, it might be in the last page, it might be somewhere in the middle, but we can calculate the average amount of time it would take, because we know the best case is it's the very first one, the worst case it's the very last one, and so the average of those two is n on 2 steps in the middle if we have n names. So we can also write this problem a little bit more formally. For a given array, find a value x inside it where the array is of length n. And our intuition figuring out the runtime here is you're at least going to have to look at all the elements to be sure that you found the thing. So in the worst case, you're going to have to look at every element in the book. And our binary search, our splitting in two algorithm, actually allowed us to get around that. So that was pretty awesome. So we talked about the worst case, the average case, and the best case, and this is going to be the way that we analyze different algorithms. So as Sharon told us, in the best case, we get O of n. In the best case, we get O of 1. In the worst case, we get O of n. And on average, it's n on 2. But as we talked about very early in class, as computer scientists, we often don't care about like the 1 on 2 out the front. It's just going to behave roughly as a function that runs in n time behaves. Okay, that's pretty good. So we can hope for the best, plan for the worst. And the reason we do this is not only because we don't necessarily know in advance the order of items that we're looking for, but sometimes there are actually users on the other side of the program who are actually able to manipulate the input that our program gets. So if you're running a directory search algorithm on the internet, if you're running the whitepages.com and you're doing linear search every time, you can imagine a malicious user who submits 30 different requests for a name at the very end of the list and ties up your computer for very, very large amounts of time. And this is in fact part of computer security, which is the field that I work in, is also designing algorithms that are safe and efficient against adversaries, people trying to act maliciously. So we saw that we could change linear search to make it somewhat faster. And this worked in the instance where the array was already sorted. So that was really our trick, was optimizing our data structure in some way. Going from just a plain old unsorted array to going to a sorted array allowed us to make a really big difference. So you'll see this next week when we start to do the analysis of the algorithm. But if we create an algorithm if we create a data structure that's sorted, then this key line over here comes into place. We can stop as soon as we've passed the point at which the name would have otherwise appeared, and we can tell whether it's actually in there or not in the first place. If we've reached a name that's later in the alphabet than the one we were looking for, and we still haven't found the right name, well, we can just stop early. We could improve even further on that by doing our binary search. And so now we're going to do another demo, and this is actually trying to do our sorting. So let me black out the screen, and I'm going to need a whole heap of volunteers. So Sharon, do you and the two people, everyone on that side of the row, all come down to the front? And you two over there in this corner? Yes, you and woman next to you and Corinna and person behind you. I think that should be the rightish number. So essentially where we are now is let me go over here so you can stay in the camera while all of you are coming down. So we're at this point now where we know that we can do better when our array is sorted, but we don't yet know how to sort the array. And this is going to be our next challenge. Okay, so everyone, grab one of these and don't turn it around yet to show the audience. Just grab one of them. And who's got a loud voice out of all of you remaining? Nope. Loud voice? Anyone? Do you have a loud voice? I don't think so. What about you two?
I don't think so.
Okay, who's got the loudest voice out of all of you? Okay, on the count of 3, we're all going to shout, hooray. 1, 2, 3. Hooray. Okay, it's one of you guys. I think it's you. Shout hooray again. Hooray. Yeah, great. Okay, so you're going to drop the card and you're going to grab the brain. And you take the card. Take the card that's fallen down. Okay, so I want everyone to line up in a big line over here.
Sorry, do I need a card?
Yes, you need a card. Okay, don't turn them around. Don't turn around. Don't turn around. That's all right. Just take it.
Yeah.
Take the card. Oh, you had it. Just leave it like that.
Yeah.
And go anywhere in the audience. Okay, so we're going to do a couple of things. So the first thing I want you to do is find the 3 of spades. Let's actually, what will we find? We will find the king of hearts.
So we'll start at
And we need a microphone for you as well. Thanks, Sharon. Before we do that, though, let's just go and get everyone's names.
Abraham,
Vanra,
So, louder.
Venera.
Elena,
Sharon.
Karina, Sijia,
Sizia? Awesome.
Nicey,
Avik.
Okay, and you were again? Tisson.
Yeah.
Okay, so Tisson's going to find the King of Hearts for us, and he's going to explain to us at the same time what he's doing. Okay,
I'm going to start with the first card.
got to keep the microphone up the whole time.
I'll start with the first card. And can I reveal it?
You can ask him.
Yeah. Can you reveal the first card for me? So it's not the card, so I'm moving on to the next card.
But unfortunately, because we're a computer, we can only look at one of the cards at once.
All right.
So Abraham, you're going to have to flip your card back around.
All right. I want you to reveal your card for me. Okay, that's not it, so you can close it. Same goes to you. That's not it, so I move on to the next. That's not it, so I move to the next. And
We found the King of Hearts, so we can terminate. Great. Okay, so turn him back around. And that was kind of the best we could do for now with them unsorted. So now what you're going to have to do is you're going to have to sort the cards. And you can come up with whatever strategy you like, but I want to see you being systematic here.
so I asked to reveal the first card. And I need to keep track of it. So
Okay, we can keep track of one card in a variable. So let's create a variable, and in it we will store the jack.
Okay. So does he close it back?
You can leave it open because we're keeping track of it this time.
I want to open the second card as well. And since I know it's lower than the jack, I switch them over.
Oh, we've got a swap. Remember the reason we introduced pointers in the first place? That was so we could do these swaps. That's kind of useful and convenient.
Yeah.
Okay, well, I guess now you guys turn them back around.
So I again ask to open the first card for me. And then I store that and go to the second card and ask to open it. And since I know it's higher than this, I changed my variable to store the second card. And
Okay, so we should close the first one then.
I asked to open the third card.
Well, Abraham, we're storing you in a variable, so we're allowed to keep you open for the time being.
And I know this card should be lower than the jack, so I asked to flip them over, switch them over.
Okay, so do a swap.
And all of them closes again, right?
Yep.
Yeah. I asked to open the first card. And then I asked to open the second card. And the first card will close, while the second card is stored in the variable. Then I asked to open the third card. And since they're in order, the second card closes, and I asked to open the fourth card. And since it's lower, I asked to flip the third card and the fourth card, and everything closes again. This is pretty heavy, ain't it?
Yeah, you know what? Do you really need to look at these first few ones again?
Yes, right? Because now the third card could be lower than the second card, right?
Well, we know that, yeah, keep going so far. There might be other methods to make this a little more efficient, but we'll see.
So first card, and then the second card. The first card will close, then the third card. And then the
Second card closes.
Fourth card. And then they will switch. And everything will close. And then the first card.
Okay, you guys are getting the hang of it. Let's speed it up slightly.
And then the third card. And then they will switch. And everything closes. Then the first card. And then the second card. And then they will switch. And then first card, second card, third card. Second card should be open. And then the fourth card. And then the fifth card.
Well, can only have two cards open, so we need to close the third one.
And then the sixth card, fifth card, fourth card will close. And they switch. Then the first card again.
We're almost through.
Third card, fourth card, fifth card, and then they will switch. Then the first card again, second card, third card, fourth card, and they will switch. And first card, second card, third card, fourth card, fifth card, sixth card, seventh card. Queen goes after king? No, and they switch, okay. And then the first card, second card, third card, fourth card, fifth card, sixth card. That's right, right?
Yep, looks good to me so far.
Card, and eighth card. All right. Okay. So you got a first card, second card, third card, fourth card, fifth card. I got to switch the last two. And then you start first card, second card, third card, fourth card, fifth, sixth and seventh switch. And first card, second card, third card, fourth, fifth, and they switch. The fifth and the sixth. And then first, second, third, fourth, fifth, and fifth switch. Fifth, fourth, and fifth. And first,
Okay, flip him back. We're almost there.
First, second, third, fourth, and third and fourth switch. First, second, third, they switch, second and third. And then first and second switch. Yeah, that's sorted. I think we need to go through and verify. So 1, 2, 3, 4, 5, 6, 7.
Okay, everyone turn them around.
And that's right.
Can we have a big round of applause for Disson? Okay, turn them all back round again. And now let's go back to your first task, which was to find the King of Hearts.
Okay. So
And
first,
you have no variables anymore. You've thrown out all the memory, so you don't know where it is.
First, open the first card, so it's not, so you can close. Second card, close. Third, close. Fourth, close. Fifth, close. Sixth, close. Seventh, close. And eighth, that's the card.
So that still required us to look through every single card in order to find the King of Hearts, which obviously wasn't the case when we did the phone book. What if we wanted to find the 6 of diamonds? How many cards would we have to look through to find the 6 of diamonds? So start this again.
All right. So in linear,
Yep, linear search.
first card, second card, third, fourth.
So we got lucky that time. Okay, everyone back around. What if I turn it? What if I want to find the 7 of spades?
Through linear.
Yep, through linear.
All right, first card, second card, third, fourth, fifth, so seventh. No, that's 8. So 9. Okay.
Wait, do you need to keep going?
No need. We can stop there because it's more than we've exceeded the number.
We can stop. So sorting did give us some advantage for linear search in that if we pass where the item should have been and it's not there, we know we can swap. But we still had to go all the way to the end to find that king. Okay, what about our other method? Do you think you can maybe replicate what we did with the phone book with the cards?
Yeah, sure, we can.
Okay, so try and walk us through how to do that.
Okay.
So what would be the first step?
Are we sorting them again? Or?
Well, they're already sorted.
All right.
We're assuming you've done the hard work, you've sorted them, unless, do you guys want to sort them again? Okay, I think we're fine.
And we're searching for?
We're searching for the King of Hearts.
King of Hearts. So we start in the middle.
Okay, let's start in the middle. So how many cards do we have? 3, 4, 5, 6, 7, 8, 9. So start roughly halfway.
At the 5th place? 1,
Sure.
2, 3, 4. Your card. Yeah, the 5th card. And that's 8. So we know it's more than. So we need to look at the other section. So
Okay, so all of you take a step back. If you're on the wrong side, take a step back.
Okay, you can close the card again. And then there are 4 cards, so I will check the 3rd card. And your card is diamond. And we're checking for?
The King of Diamonds.
Okay. So we know that should be more than that, so you can close the card and they can be
Yep,
more.
and the other 2 of you can step back because we know the card isn't there.
And
King of Hearts, sorry.
And then we come to the card. So 3.
And we found the King of Hearts. So how many steps did that take us?
3 steps.
only took us 3 steps to get all the way to the King of Hearts, when previously using linear search, we needed to go through all of them, and the only advantage we had was we could stop early if we found that it was somewhere in the middle and it would missed it over. So can we have one more round of applause? That's really awesome. Okay, everyone come back to level. We're almost done. You still need your brain for one more minute, because we've got a bit of a final quiz coming up. So come back over here.
Okay.
So I thought that was brilliant, but tell me, how did you do it? How did you do that sorting? I was pretty impressed. Stand over here at least so we can get you in the camera as well. Tell me your thought process. What did you do?
So I broke down the list to like smaller chunks and I sorted 2 at once. It's sort of like how you do binary representation. You go back to what you were, like the beginning card, and then you go through until you meet something which mismatch, and then you sort that, and then you have to come back again because that mismatch card could be the first card to go over and over until you meet the last card.
So tell me if I'm getting this accurately. So what you did is you started at the beginning and you went along till you found 2 cards that were out of order. And we know how to check if 2 things are in order in C. We have the greater than sign and we have the less than sign, so we know how to compare, is A greater than B or is B greater than A? So we did that, and then if they were mismatched, what did we do?
We swapped them.
We swapped them, and then what?
And we have to start again from the beginning.
And then we started again from the beginning. So our process is to go through, look for a mismatch, then come back to the beginning, and so if there's a mismatch, swap them, come back to the beginning, do the same process again and again and again. What is the number of times that we have to do this? So how many times did you have to go through the entire thing? As a proportion, how many times did you have to go through the entire thing relative to the number of cards that there are? So let's say that there are n cards. How many times do we have to go through and look for these mismatches?
N factorial?
N factorial? Not quite. So let's say that for a given card, so Corinna, do you want to step out the front? How many different places could Corinna be mismatched with?
N.
She could be mismatched with n places. So for Corinna, we'd have to do n swaps. Then what about, in your process, we were swapping her somewhere, so just swap yourself somewhere into the middle, doesn't really matter for the time being. Okay? And now we're starting again at the very beginning of the list. How many swaps would we have to do for the person at the new, well, let's say Corinna was at the end. What was your name again at the? Nancy. So how many places could Nancy be mismatched?
N places?
Well, not quite n places, because Corinna, we already know that they've swapped, so they're in the right order. But other than Corinna, she could be mismatched with any of them.
Yeah.
So there are now n-1 places that she could possibly, n-1, or sorry, n-2 cards, because she can't be mismatched with herself. So can't be n, it can't be n-1 because Corinna is now in the right place relative to her, but it could be n-2. So we have n-1 by n-2. Okay, so swap yourself somewhere in the middle, just arbitrarily. And we know Corinna's already fine, so let's ask about Abraham. How many places could Abraham be mismatched with?
N-3.
N-3. So now I'm getting n-1, n-2, n-3, and we're adding them up, right? Because for each of the cards, that tells us how many swaps they're going to do. So how much is that overall? So let's throw away the -1, -2, -3, because we're lazy computer scientists. So I've got n plus n plus n plus n plus n plus... How many times are we doing that?
If there are 8 cards, 8, 10?
Well, if there are n cards.
Okay, n times n squared.
N squared. So this gives us an n squared algorithm for sorting. And can we have one more giant round of applause for all of our lovely volunteers, and for Tissan in particular? Thank you very much. Okay, you can resume your positions. And what we have actually discovered is a very simple sorting algorithm. Now, there are a whole bunch of different sorting algorithms we will do in class. Based on what I saw, I'm pretty sure we were doing a sort called bubble sort. Now, every year it's a little different. The student who comes to the front gets to pick whatever sorting mechanism they like. The algorithm changes every year. Someone picks something different. So we will go through a few of these interesting sorts over the course of the semester to figure out what are all the different interesting ways that you guys could have picked a sort. They'll have different behavioral characteristics. So we saw this one was n squared, but all of you are good algorithmaticians now, so you're probably asking, can we do better than n squared? So I'm going to put my big brain on. This was me in the office earlier today, and we're going to see if we can write our bubble sort. Now I will switch this over in a second. So the first thing you'll notice in here is we have our int swap function. And this is, of course, absolutely necessary because the core thing that we were doing, the thing that made our sorting algorithm work, was our ability to swap. So this is why pointers suddenly come in handy, because we are going to want to have a sorting algorithm overall. And so here's my sorting algorithm. But a key part of the sorting algorithm is this swapping function. And it would be really annoying if we had to write all the swapping code inside the sorting function, and then the sorting function would be forced to do all the logic for all our program unless we had some way of actually returning the sorted array, of actually working on the memory addresses of the thing that we actually wanted to change. So in order to do a swap, we needed to use pointers, we needed to use memory, and this is where it's all coming together. I told you I'd die at some point during today. So let's look at the core bubble sort algorithm, what we just did. So we're going all the way from the start to n minus 1, and then compare adjacent elements up till n minus 2. So this is actually slightly different from the process we just did, because instead of going all the way back to the beginning every time we find a mismatch, we can just keep going along the rest of the array and looking for more mismatches. So we didn't actually have to reset. 1 second, Shah. What we could have done is, I should have done this when everyone was out here. What we could have done is we go along, look, 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 okay, there's a swap here, keep going along, look, 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 is there another mismatch? And then when we find the mismatches and we're done with those, then we start again. So that's really a slightly cleaner version of the algorithm that Thyssen came up with. So that's what we're doing. So starting from picking the first card to compare things to, and going all the way up till the second last one, compare two adjacent elements, and then swap them if they're in the wrong order. You repeat this process over and over again, n squared times at worst, or O of n squared times at worst. We know we fudged the math a little bit, and then it works. So let's put that all together. Let me just get in the right directory, because this file was in the wrong place. And this was my initial starting array over here, A, and let's give that a run. So before sorting, after sorting, it seems that this is a really, really simple program, but it's taken us all of our C knowledge thus far to get to this point. Now we'll spend a few more minutes going into a few of the details, syntactic details of this program, and then I will be leaving you for the rest of, for the next 2 weeks until just after the semester break. Okay, so the first thing we do in this program is we are creating an array using our array syntax. Now remember, we could have just as well have written this using pointer syntax, but we are writing it in this array syntax, and here we don't have to specify how large the array is because the compiler is going to automatically pick it up from the number of elements on this line. However, if we tried to do this, it wouldn't work. With C, you can only give it all the items if you're doing that at the time that you create it. If we wanted to do it the other way, we'd have to do, how many items are there? 7. We'd have to do like this, and then A0 equals 8, A1 equals 7, etc., etc. So that's that bit of syntax. And then the other thing that I'm doing is this time, instead of putting like a 0 at the end of the array to mark where it finishes, I'm actually just going to store how many items there are. And this will allow me to skip having to have what we call a sentinel value, or a value that tells us when the array is going to end. So then I am going to have a print array function, and let's take a look at that. Our print array function takes in 2 inputs. It takes in the array, and it takes in the length of the array. And then it's just going to do a basic for loop from 0 up until the length of the array, printing each item one by one. Okay, so there's that. And then it calls bubble sort. and bubble sort both has to have both the array and the length of the array. We hope that it works, and then we print it again. Now, Shah had a question.
Is insertion sort and bubble sort the same thing?
Insertion sort and bubble sort are kind of similar, but they're not identical. We'll maybe leave some of that for a bit later. Now, one question you might have is why in bubble sort did we not have to actually deal with the pointers explicitly? You'll notice that I haven't actually used pointer syntax in bubble swap at all until I get over to passing it over to the inswap function. Why did I not have to pass the pointers to things around, even noting that when I got back to main, the array inside main had changed? There's something special about arrays that made this possible? Okay, in the glasses in the middle. Let me get you a microphone. What was your name?
Nathan.
Nathan. Okay, so what is it about arrays that allows us to just pass them around and have the changes reflected back in the calling function?
Is it that arrays are already pointers?
Yeah, arrays are already pointers. And so by passing arrays around, if we use an array as an argument to a function, we're essentially passing a pointer around. We're passing an address around. And so when we use or modify elements of the array, we're already doing that step that we had to do of figuring out where in the computer's memory we're coming from. Thank you very much, Nathan. But that still leaves us with a little bit of a mystery, because we are using the address of syntax right when we get to the inswap function. Let's put that back in. Right when we get to the inswap function, we've taken the address of two of the elements in the array, the jth element and the j plus 1th element. And the reason we have to do that is, let's look at our intswap. Intswap takes two pointers. And what are we actually passing it? We're passing it the address of the jth element and the address of the jth plus 1 element. Why? Well, what would happen if we just did that? Well, the jth element of the array is not a pointer. Even though it's inside the array, the jth element itself is just one of these numbers from up top. So what you actually want to know is, if we're trying to swap these two things, you want to know the address of the second element, of the third element at index 2, and the address of the fourth element at index 3. And that's why when we call intswap over here, we're actually going to put in the ampersand over there. So at the end of the day, we're left with one pretty clear message about arrays, and that's that they are all memory. And by recognizing these different abstractions, it enables us to actually perform algorithms in either faster time or slower time, or structure and design our memory such that our algorithms are efficient. Now, it's a trap. This is now, I think, the fourth or fifth big trap we've encountered in lecture. C does not check whether you are accessing an element that's actually in the array or not. So let's say you've created an array of 5 elements, and you ask for the element at index number 5. Now, I forget who it was, but someone earlier today already told us that you can't access element number 5 because if we start counting at 0, the 5th element will be at space number 4, at index number 4. So if you access array element at index 5, you're going outside of the memory that you've actually set up. Now what happens? Well, a number of things could happen. You could mess with the memory that belongs to another variable somewhere in your program. You could mess with something even more important. And if you go outside of the memory with which you've been given permission, what do you get? Segfault. You get a segfault. And so this is one of the more common issues that we'll see, particularly in student code, but also in real-life developer code, that leads to problems, is people accessing outside the bounds of the array. And in fact, this is also what leads to a very large number of exploitable errors in programs. So vulnerabilities, mistakes that people have made, bugs in the code that actually allow hackers to get in and take control of the computer. Now you might think, okay, why does accessing memory that I potentially don't have permission to allow hackers to take over the computer? We'll now imagine that your hacker has managed to manipulate parts of their input, and they've put some input in at that location, and you're accessing it expecting that it's something that you controlled. Well, if the hacker is clever, they can change the way the decisions that your program makes by strategically choosing the values in that location which you accidentally were accessing by mistake. And more on that if you come take my third year information security class. And with that, I will see you in another 2 weeks. Enjoy the next 2 weeks with Janjong, enjoy your semester break, and I will see you all soon. Thank you very much.